Okay, in this example, we're just going to think about how we've solved some equations in the past and how we're going to solve an equation that we've been looking at for this unit. So if you look at the first equation, we've solved many equations like this, where it might be in the form of 2x plus 4 equals 0, just using basic inverses on both sides. So for this first one, we would simply just divide by 2, giving us x equals 4. The second one was a little bit harder, but we have done this already using a property, essentially square rooting both sides to get rid of the radicals, because the opposite, I said radical, to get rid of the exponent, because the opposite of an exponent is a root. They're inverses and cancel each other out. But because this is an even root, we need to consider both the positive and negative versions of the answer. Now, this last one here is a little bit different. A root cancels out the exponent, but what cancels out the base? The number that has the exponent. And that's what this second part of the unit will revolve around in solving this type of equation and exploring the feature that allows us to do that. The type of expression that allows us to do this is called a logarithm. Log base 2 will cancel out 2 to the power and will enable us to actually solve this equation, giving us x equals 3. Now this one you could have solved pretty easily just by guessing and checking, but if you want to apply this to actual situations, you wouldn't necessarily be able to do that efficiently. So this will allow us to have an efficient method of doing that, as well as other properties that allow logarithms to be useful in different situations. Okay, so logarithm of base b of x is defined as follows. If we have log base b of x equal to y, that's if and only if b to the power of y is x, with the conditions that b is greater than 0 and not equal to 1. Those were the conditions for exponential functions, because, well, it wouldn't be a function if it had some of those properties, and it wouldn't be very interesting to explore. More so, it would not be continuous, and you would get some crazy behavior if b was less than 0. So that's why we exclude that. And b equal to 1 would be very boring, because that would just be a horizontal line. So yeah, those are excluded as far as exponential functions go. And then we also have to look at x values greater than 0, because we can't take a logarithm of a negative number, because a number to any power should be positive, with the exception of odd roots, if the base is negative, but the base is excluded from being negative, so the result can't be negative. So that was a little bit rattled on there. But just based on the exclusions for b, also extends to creating an exclusion for what values x can be. Just to kind of look at the logarithms formatting before we go on. So the formatting here, this base is a subscript. In terms of the exponential, the base is still the same. So the base is the number with the exponent in an exponential. It's the subscript here in a logarithm. They're both referred to as the base. The x here, which is what's inside the logarithm, is the result of the exponential and of exponential. So you can see that is right here by itself, result of the exponential. And the last thing, the y, is the exponent in the exponential. Logarithms essentially tell you what power you raise the base to get the specified number. The result of a logarithm is the exponent. Okay, in this example, we're going to look at changing the forms from logarithmic to exponential or vice versa. In part A, we're going to change from logarithm form to from exponential form to logarithm form. So we have the exponential already there, and the formatting for logarithm goes as follows. The base is the subscript. The number that sits here is the result of the exponential. And then the number on the other side is the exponent. So the base is the number 3, so it's our small subscript. The result, which is by itself for the exponential, is 81. And then the exponent is the result of a logarithm, and that is 4. So there we have it. For the second one, we're going to write it in exponential form, as it's a logarithm. So we have the base, we have the result of the exponential, and we have the exponent. So we have 10 to the power, the exponent is 3, and the result of the exponential is 1,000, which should make sense because 10 to the power of 3 is 1,000. Okay, in this example, we're going to look at how to actually find the value of logarithms. So as I go through this, A here, log base 5 of 625. Now, a logarithm poses the question, what power do you raise the base to get this number? So what power, 5 to what power, is 625? That is the question that a logarithm poses. Well, if you don't know the answer to that, just like in elementary school, when you were trying to figure out divisions, like 25 divided by 5, you would go, oh, hey, I don't know that. You would go 1 times 5, 2 times 5, 3 times 5, until you find 5 times 5, which is 25, and you would know that the result is 5. Well, in a similar fashion, we do the same thing for logarithms. When we're trying to figure out the exponent, we'd do 5 to the first, 5 to the second, 5 to the third, 5 to the fourth, and once we get to 5 to the fourth, my little carrots there are kind of horrible right now, but once we get to 5 to the fourth, we see that it's 625, which means the result of taking log base 5 of 625 is 4, and the answer is 4. Now, I do want to just take a side note here. I have a lot of students that I have seen writing this, saying that this is the answer. And I do believe it's an important distinction to note. We represent our thinking like this to figure out what the logarithm is, or the value of the logarithm is, but this is not the answer to evaluate the logarithm, just the exponent is. We use this expression to help us figure out what the number is, to represent that thinking, posing that question, 5 to what power is 625? So I believe that's an important distinction, that the answer is 4 and not 5 to the 4 equals 625. Second one here, doing the same thing. 4 to what power is 64? And if you know your exponents from radicals and stuff, it may be a lot easier. You can probably jump straight away to 3. And if not, just go through the same thinking. 4 to the first, 4 to the second, and 4 to the third. You would eventually find it, or realize that you've passed it and it's not a perfect power, and either need a calculator or just approximate it. Now the next two are a little bit different. So for C here, C, it's log base 2 of 2 to the power of 8. So what this asks us is, what power do we raise 2 to get 2 to the 8th? Which, if you look at that closely, it kind of seems like a pointless question, because we have 2 to the power on both sides. So what exponent needs to be there? Well, simply 8. And as we'll discuss further, log base 2 and 2 to the power, they are inverses. That's part of the whole point of logarithms. why we do them is so that we can cancel out the base that has an exponent. So we'd see later that they cancel out, leaving us with just the 8. This one here, D. So D, log base 3 of 1 over 9. Well, for log base 3 of 1 over 9, we are going to do the same thing. But you might be thinking, what power? Like if I do 3 to the first, 3 to the second, I'm just going to go up 3 and 9. We're not going to get 1 to the 9th. Or 1 over 9, I mean. But there's something you might be forgetting, and that's negative exponents are reciprocals. So if we realize that 3 to the power of 2 is 9, then 3 to the power of 2 is 1 over 9. Or it's not 2. Negative 2. 3 to the power of negative 2 is 1 over 9 and not negative 9. So the answer for this one would be negative 2. And if you don't believe me, you can type it into the calculator, which would give you the decimal 0.1111 repeated, which is 1/9 as a decimal, but negative 2. So pretty handy. You can find the power like you normally would, and then just change it to negative for the reciprocal. One more case I want to talk about is this case. So log of, I want to go 25 of 5 equals what? So this is just an extra case here that I have in the practice that I give my students as something to think about. This is a little bit different because it's really hard to imagine. A lot of times people overlook what exponent do you raise 25 to get 5. So I tried to walk them through it in a reverse way. I have them go and figure out the exponent for 5 instead. So 5 to what power is 25? That's a lot easier to handle. 5 to the second power is 25. And then just keeping with that logic, well, this is the opposite direction of what we were trying to aim for. And what is the opposite of an exponent? Well, the opposite of an exponent is a root. So let's go and look at it like this. The square root, with the index being 2, of 25 is 5. Now, since we're focused on exponents, let's take this one step further. How do you represent the square root of 25 as an exponent? Well, for fractional exponents, or for radicals, turning them into fractional exponents, it's exponent over index. The exponent with 25 is 1, and the index is 2. So the answer would be 1/2. That's just a little exercise that can be helpful. And as soon as you realize that, it becomes a lot quicker to actually do these ones, but that's just how I walk them through it when they first try to do it themselves. So in this next section, we're going to be talking about evaluating logarithms again, but we're going to be using the calculator. Now there's two special logarithm buttons that most calculators have. There's the common logarithm, which is implied to be base 10, which is represented by just log x. And then there's the natural log, which is log base e, represented as ln of x. Log base 10 means the same thing as log x, and log base e means the same thing as ln of x. So this adds a little bit more to the list of implied numbers that we have in mathematics. So just as a rundown of some of the implied numbers that we have, right now we have a coefficient is implied to be 1, an exponent, if there is none, is also implied to be 1. If it's a radical, the index is implied to be 2. And now we have two more implied numbers that we'll be using. If it is log of x, it's implied to be log base 10 of x. And if we have ln of x, it's implied to be log base e of x, which you'll often see a lot of people just write the e down below, myself included. So where do we find these on the calculators? And most calculators, see if this will work, not the best lighting for this. Most calculators have them right here, somewhere on the calculator. And if you look really closely, it might be hard for my camera to zoom in. There we go. If you look closely, you can see that right above the log key is 10 to the power of x, and right above the ln key is e to the power of x, just reinforcing the basis. If you look at some of the other keys that you might be familiar with calculators, a lot of calculators are designed in the same fashion. Keep going out of focus there. The x squared key and its inverse, the square root, are right on top of each other. Same thing with a general exponent and the general root key. And if I can get it to zoom in or focus in on the trig functions again, sine and sine inverse, cosine, cosine inverse, tangent and tangent inverse. A lot of times calculators are designed so that their inverses in the original are on the same key. So it's a handy way of remembering the basis if you ever do forget. And as a side note, back before calculators, people actually used reference tables to actually go through and find these. So yeah, just in case you were curious. And here's just a quick reference table that I just Googled for logarithms. You can see that there's a bunch of different numbers on here. And I've used them before, but it's been very long since I've done that. So if you're curious about how to actually use one of these tables, try looking it up. But they used to be used for sailing when they were invented because they had to do large calculations, and logarithms turns large multiplication problems into simple addition just using these tables. So they can be very handy, especially during sailing, which not many people do without a calculator or navigational equipment anymore. But just one of the few history facts I actually do know. Okay, so in this example, we're going to use the calculators to find the value of each logarithm. Now, I'm not really going to type it in the calculator because I really don't have a setup for that for my handout calculator. I could pull up Desmos, but I just kind of want to explain how to actually go through and do it. So for the first one here, it's log. Most calculators have a regular log key. So if you just click on the regular log key, it will come up in one of two fashion, or one of a couple factions. So it might come up like this, or like this, depending on how your calculator is set up when you click the key. Now, if you have a calculator that doesn't do order of operations, for example, the calculator that is on the iPhone, I'm pretty sure that's one that doesn't do order of operations for you. You actually have to type the 900 in first and then hit the log key. Because it doesn't actually follow order of operations, and when you hit the log key, it will take the log base 10 of whatever numbers typed into the screen at that moment. But if your calculator does order of operations, you simply hit the log key, and then if it's a setup like this, parentheses are already included, so you just type 900 in. And if it's a setup like this, you may need to add your own set of parentheses. For just a normal number, you don't. But if you have to type in an expression inside the logarithm, you would. So you would just type in 900. And either way, no matter how your calculator is set up, if you type it in correctly, and we round it to 3 decimal places, we should get 2.954 rounded to 3 decimal places. For ln of e, the calculators would be set up sort of the same fashion. If your calculator was one of these three formats, then you would want to type it in appropriately, hitting the ln key followed by E. Some handheld calculators, like the one I had on the video earlier, when you type in the E, it will spit out this, e to the power parentheses, because it requires an exponent for some of the calculators for E. Well, since this E doesn't have an exponent, it's implied to be 1, so e to the first, which gives us, if you type it in, 1, and that should make sense, because remember, logarithm asks you what power do you raise the base to get this number, and this logarithm is log base e, so it's really asking you what e to what power is e to the power of 1, so it should make sense that when you type it in, you get 1. By the way, on that note, if you go back to the other one, that's saying 10 to the power of 2.954 should be about 900. Now, it won't be exactly 900 because we did round it, so that kind of throws it off a little bit, but it would be very close to 900. And if we do the last one here, if you try to do this, one of our conditions for logarithms was that the number inside the logarithm is not negative. This is asking us the question, e to what power is negative 1.87. And e is a positive number. A positive number to an exponent cannot give you a negative number here. So this is an impossibility, which means this just does not exist. Most calculators might say something along the lines of domain error, just because you can't plug that into the inside of logarithm, which is where x is referred to as. So yeah, that's evaluating with the calculator. Okay, so in the next example, we're going to be solving an equation. Now, there's a note up top for my students in particular. I have a general rule. If I don't tell you where to round, just keep 3 decimal places. For the most part, I prefer fractions anyways. So if I don't tell you where to round, or if it wouldn't make sense to round to 3 decimal places like money, it doesn't make sense to keep 3 decimal places for money. So in situations where I tell you, or it doesn't make sense to round otherwise, keep 3 decimal places. So with that being said, 25 equals 10 to the power of x minus 1. The ones we're solving in this lesson are just going to be simple ones that we can do with the process of reverse order of operations. Please excuse my dear Aunt Sally. So exponents, which is actually going to be the base in this case that we're going to get rid of, will be at the same level as normal. But remember, we can't touch the stuff in parentheses, which would be the stuff inside the exponent, until we get rid of everything else. So we would first get rid of addition and subtraction outside of the exponent. There is no addition and subtraction on this one. Multiplication outside the exponent, we have no multiplication. That would usually sit here. Exponents, and in this case, the base. So we want to get rid of the base. We're going to do that since it's base 10. We're going to do that simply by taking log base 10 on both sides. Log base 10, in other words, just log. Log base 10 and 10 to the power are inverses. They cancel out, and we're left with x minus 1. On the other side, log base 10 of 25. Now, I don't know what that is off the top of my head, but I can easily type that into a calculator and get 1.398 if I round to 3 decimal places. And then if I finish it off by adding 1, 2.398 is the value for x. And there we have it. In this example, we're going to be solving a logarithm equation doing the same sort of process. First get rid of the outside stuff, then exponent or the key step, and then finish solving. So in this case, there's nothing outside the parentheses. And just as a reminder, since we are just starting to talk about logarithms, for logarithms, the stuff immediately after, the term immediately after is considered to be inside. So in this situation here, just the 4x would be inside. Since there's no implied parentheses, or since there's no parentheses, the implied set is just for around that next term, the following term. But there has to be something inside of a logarithm. So there has to be something following the log base 4, or whatever the logarithm happens to be. With that being said, nothing is outside this logarithm, so we're going to go ahead and get rid of the logarithm. Now, ln is log base e, and to cancel out logarithm, we're going to make both sides an exponent of e. Log base e and e to the power cancel out, leaving me with 2x plus 3 equals e to the power of 4. E to the power of 4, if I type it into my calculator, is approximately 54.598 if I round to 3 decimal places. And then it's just a matter of solving whatever's left. So we'll subtract 3, get 2x equals 51.598. And then finally, divide both sides by 2. X equals 25.799. And there we go. Okay, so going through and solving this equation, doing the same process. So get rid of anything outside the exponential first. The exponential is the number and its exponent. I can't touch the stuff in the exponent until we get rid of the base, which means we have to get rid of everything else first. This time we do have something else, so we do have that plus 1, so we're going to start off by subtracting 1. We'll have 2 to the power of 5x minus 9 equals 32. Next, we're going to go ahead and get rid of the base by doing a logarithm. Remember, the opposite of the base, or to cancel out the base, we need to use the inverse of an exponential, which are logarithms. So we would do log base 2 on both sides. Log base 2 and 2 to the power cancel out, leaving me with 5x minus 9 equals, well, log base 2 of 32 is 5. Remember, logarithms pose the question, in this case, 2 to what power equals 32. Well, 2 to the 5th power is 32, so log base 2 of 32 is 5. From there, it's just a two-step equation, plus 9, so 5x equals 14. And divide by 5 on both sides. X equals 14 over 5, or 2.8 as a decimal. There we have it. Okay, in this last one, we're going to solve an equation, but we're going to do it in the exact format. Now, what I mean by an exact format is in some cases with exponentials, because we're relying on the calculator to do certain things, such as these ones up here that were done earlier, we had to round. Now, this one we didn't have to round because it did happen to be a perfect power, but in some cases we do. But what if we want the exact answer and not round? Well, we can do the same thing, or we can do that as well. It's just basically like solving a literal equation. So for this one, we get rid of anything outside the logarithm first. In this case, divide by 5. Giving us ln of 3x plus 2 equals, well, 60 divided by 5 is 12. Next, the opposite of ln, or log base e, is making both sides an exponent of e. Ln and log base e cancel out, So we have 3x plus 2 equals e to the power of 12. Now, I could type this into the calculator like I did before, but I would have to round it. So that would make it not an exact answer. So we can leave it like this. Now, if it's something that you can do without rounding, you should do it as far as exact answers go. So like 2 to the power of 5, I should be able to do that. So I can type that into the calculator if I need to and move on from there. But e to the power of 12, I would have to round. So we're just going to leave it as is and solve from here. So subtract 2. 3x equals, well, I don't know what e to the power of 12 is, so I can't really subtract 2 from it. So e to the power of 12 minus 2. And then finish off by dividing by 3. Dividing by 3. Again, I can't really do that, so the exact answer could be written as e to the power of 12 minus 2 all over 3. And there's other ways I could write the exact answer. Exact answers rely on the fact that you are not rounding anything along the way. But if it is an operation that you can do, you should do it.